Okay, so we are on to Chapter 7, in which we're talking about information criteria, informational entropy. This is a very interesting topic. I believe that its genesis was based in communication. How do you send messages across kind of an unreliable or a noisy communication channel? But it just so happens that there are some very interesting applications for statistics. Before I get going here, this book does a good job of giving you what you need to know to get through some of the applications for information theory. But if you want to know more, there's a couple of books that I would recommend. One is by a man named Applebaum, and the other one is by a man named Stone. And so there's links to the Amazon versions here. I'm sure there's PDFs that you could find out there, but anyway, these are both very good, and they are understandable. There are some other highly advanced, or I shouldn't say highly advanced, but more advanced, kind of harder to get through textbooks, such as I think it's Cover and Thomas, The Elements of Information Theory. You'll see that one bandied about. But it's a slog. You have to be very good at these things to be able to get through it. So these are two very approachable introductions beyond what you get in the Rethinking book here. Okay, so anyway, we want to answer the first question. So we want to state the three motivating criteria for informational entropy, expressing this in our own words. Okay, and so we will get to those here, and then I've even added a couple that are not mentioned in the book or maybe implied in the book. But first, I just want to march through the equation for entropy here, okay? Because it can be a little bit befuddling when you first see it. So I want to break this down. And so for this first pass, we're going to ignore the logarithm, okay? So let's just look at this parenthetical term here, okay? So we have 1 over the probability that x equals some value, little xi, okay? And so we can think of this term as being surprise, okay? So think about this. If a particular value of x is very probable, say 99% probable, well then 1 divided by 0.99 is a value that's pretty close to 1, okay? And so that's going to be some level of surprise, and it turns out that that's not going to be very surprising, okay? And hopefully that makes sense. If a very probable thing happens, it's not surprising, okay? But now let's take little x to be, the probability of little x to be very low, right? So a value of x shows up, and it's just not very, it doesn't come up very often. Well, then this denominator is going to be very small, and so 1 over a small number is a big number, okay? There's more surprise, and again, intuitively, that should make sense. The less probable something is, the more surprised we are when it happens, okay? So that's the surprise term. Okay? And again, we're going to skip the log part for right now, and then we're going to come over here, okay? And now this function, or this term right here is, we can think about this as a weighting function, okay? So how often should we expect to be this surprised? Well, we should be that surprised, right? We should be this surprised over here at the rate at which that value is occurring, or at the rate at which that event is happening, right? So let's walk through this. So again, if we have a very probable event, we'll say x, the probability of x is 0.99, okay? We're not going to be very surprised when that happens, and that event is going to happen a lot, okay? Now, when we have an improbable or a less common event happen, we're going to be really surprised, but by the fact that we're going to be really surprised when it happens, it's because it does not happen a lot. Okay, so there's this kind of teeter-totter effect that's taking place. The more surprised we are, it is because it happens less often, right? And so this term right here is weighting our surprise. And so then we should ask, okay, well, over all values of x, how surprised are we on average? Okay, well, to do that, we just simply sum up these weighted surprises. Okay, and that's all we're doing. Okay, is for a variable x, how surprised are we going to be as we kind of look at the different values of x come up? Okay, and that's all that it is. Now, finally, the logarithm here. Just when we get into the desirable qualities of our measure of uncertainty or of entropy, the logarithm helps us accomplish a bunch of those things. Okay, so we'll just think about it as a little bit of an ornament for right now. Okay, now to get from this equation to this equation, all that I'm doing is, it's just some notational trickery, but if I take this fraction, the log of that fraction, I could rewrite that as being the negative log of the probability of x equals x. Okay, and so there should be a negative here, but it's just been moved out front. That's all that's happening there. Okay, so here's that negative out front, here's that negative out front. And now, as I said, entropy is just a weighted average of surprise. And so the average is expectation. That's the expectation operator. Okay, so that's just our average of this term here. Oops, of this term here. Okay, so that's how we get from all the way to there. Okay. All right. So there's some desirable features that we want in a measure of uncertainty. Okay, so one is continuity. So in other words, as our level of certainty moves up and down, we would like it to be able to move up and down to any value between completely uncertain and completely certain, right? We wouldn't, well, yeah. I hope that makes just intuitive sense, right? And this formula accomplishes that because it is a function of probability, and probability is a continuous function. It goes from 0 to 1, okay? The next one, I'm calling proportionality. I don't think it's called this in the book, but I just needed something to put in boldface here. But proportionality means that all else being equal, as there are more possible values for random variable x, right? So as there's more, as n gets bigger, okay? Well, actually, it's not as n gets bigger, but as there are more possibilities for xi, or for x, right? Then entropy should increase. Okay. So hopefully this makes sense. So imagine that there's two options for big X. We'll call it x1 and x2. Okay. So to find the surprise for both of those, we would just enter them here, and then to find the entropy over x1 and x2, we would just take the weighted sum of all of those. All right. But now imagine we discover that there's actually a third option for xi. Okay. Well, now what's going to happen? Well, the first thing that's going to happen is, of course, now instead of having two terms to add together, we're going to have three. Okay. So already we see that there's this tendency for entropy to want to go up because we're adding three things together instead of two. But also when we added a new option for x, the probability of each option has to adjust, right? So before we had two options, okay? And so let's just say that they were equal probability, or we said that they were equal probability, so it'd be 0.5 and 0.5. Well, now we have a third option in here, and now we'll just say that they're all 0.33, okay? The probability of each of them is a third. Well, then that means that the surprise of each of them has gone up, right? And so, of course, that means that there's going to be more informational entropy because we have more options for x. Right? Now, the last one mentioned in the book is additivity. Okay, so in other words, if I have some amount of uncertainty about x1 and some amount of uncertainty about x2, right, then my uncertainty over both x1 and x2 should be the sum of those things. Okay, so the book is using probability of rain and probability of no rain, basically, or of sun or something like that. And so I would like to say that my total uncertainty about the weather is the sum of my uncertainty about each weather event. Okay, and of course the formula here is accomplishing that because we are summing over our surprise. Okay? All right. Now, there's two more that the book doesn't mention that I will mention here, and then there are many others that could be derived from this formula or whatever. But let's just mention a couple of these. One is non-negativity. So in other words, entropy cannot be a negative value. All right, and intuitively this is desirable, right? Because we wouldn't think of having negative uncertainty. We can only have zero uncertainty, which is the state of being completely certain. All right. We accomplish that because by a couple of different ways. One is because probability is a positive function; it doesn't go below zero, and also by adding logarithms. Logarithms are never below zero. Okay, so we can never have zero, or we can never go below zero. We can have zero uncertainty, zero entropy. Right, and that's when there's only one option for x to be, in which case it's not even a variable anymore, it's just a constant. Okay. And then the other one is maximal value. So entropy has a maximal value, and that what the maximal value will depend on how many options x has. Okay, and but maximal value, or I'm sorry, the maximal entropy occurs when the probability of each option or each value of x is equally probable, right? So if I have, let's just take a coin flip, heads and tails, and we'll say that they're equally likely, okay? Well, I'm maximally uncertain when heads and tails are just as likely to come up after the flip, and that should make sense, right? I'm most uncertain when they are equally probable. But now if I have a weighted coin, let's say it comes up heads 75% of the time, well, then I'm going to be less uncertain at each coin flip, okay? And so the maximal value was achieved when all options of x were equally probable, okay? And so the maximal entropy distribution is a uniform distribution. Okay, so now there's a caveat to what I'm just saying here. There is another concept that this chapter will address, and it's a very interesting idea, called max-ent, or also called maximal entropy. And the way that it gets used in this idea is that the maximal entropy that is achieved given some set of constraints about our probability distribution, right? So you can think about it as taking a uniform distribution and then applying things to it that you know to be the case, or assume to be the case, or think are probable, and that uniform distribution being kind of morphed and constrained in certain ways. So given the constraints of maybe prior knowledge or whatever, or certain assumptions, max-ent is the maximal amount of entropy given this set of constraints. So please don't confuse the fact that there is a maximal value of entropy and it's the uniform distribution with there's a maximal amount of entropy allowed under certain assumptions. Okay, that's what max-ent is called. Okay, like I said, there's a lot of other things that you could derive from these formulas. Okay, and if you want to learn more, again, I would check out these resources. Okay, thanks.